All right, so now we're going to start looking at the heating curve when we apply numbers to it, like the actual temperature and the heat added. So looking at this, we're looking at water, right? So the heating curve for water, we know melting is at 0, boiling is at 100. Again, note that look at the line for boiling versus melting. It takes a lot more heat down here to heat water than it does, or to, vaporize water than it does to melt water. Okay? So now we have this thing called calorimetry. Calor and heat, or calor in Latin means heat. The measure of heat changes associated with chemical or physical change. The heat amount will often be indicated by a temperature change. This is where you get this formula QM Q equals heat or in joules. If you are confused and you're like, okay, miss, I am never going to be able to remember this formula. It is on the back page, table T, and you have Q equals MC delta T, and it does list these lovely things: heat, mass, specific heat, and change in temperature, and it even gives the units that go with it. The big thing is you got to know is when there's a temperature change. So that means only when it's a solid, only when it's a liquid, only when it's a gas. It is not when it is changing, doing the phase change. Okay? So what the heck is specific heat? The C thing. Okay, so specific heat is the amount of energy required to raise the temperature of a unit mass, 1 gram, 1 degree Celsius. It's how much it takes to change 1 gram, 1 degree. The higher the specific heat, the more energy required to raise the temperature. So one thing to note that most metals have low specific heats, meaning they're easy to heat. For instance, aluminum right here has a 0.903 joules per grams degrees Celsius, whereas copper has a 0.38 joules per gram Celsius. Both metals both have relatively low specific heats. But water, being an enigma on its own, a very special thing, its specific heat is 4.18 joules per gram Celsius. Now you can see that is a lot more heat, or it's a lot more heat needed, or a lot more, pardon me. Yeah, it's a lot more heat per gram needed than metal or copper, which is why we use metals and coppers in our pans to help heat the food, or, for instance, water. Water is difficult to heat, and substances high in water content, like the human body, maintain a stable temperature because it takes so much heat to increase it that our bodies have a stable temperature most of the time. All right, so here's an exercise. How many joules are needed to raise the temperature of 50 grams of water from 25 degrees Celsius to 55 degrees Celsius? All right, so we got to start plugging in the numbers to this formula, again found on table T. So M is your mass. It gives you a mass of 50 grams. So all I have to do is plug in 50G right here. I need specific heat. Oh, but Miss Co, it doesn't give me specific heat. But it does, because it says water. And on the front page, table B, you will find the specific heat for water, which is 4.18 joules per gram Celsius. Okay, so the last thing we need is change in temperature. How do I get that? All I have to do is take my two temperatures, subtract them, and I get 30 degrees Celsius. Now here's the easy part. All I got to do is multiply. When I multiply, I'm looking for joules only. How do I know I only get joules? If I go to cancel out, I've got grams over grams, so my grams cancel out. Celsius over Celsius, Celsius cancels out, so I'm left only with my joules. When I plug in all those numbers, I should get 6,270 joules. All right, let's see another one. If I have 45-gram cylinder of a metal, so I don't know the specific heat, undergoes 10 degrees Celsius temperature change. Awesome, I don't have to subtract anything. With an addition of 203 joules of heat. There's my heat. What's the specific heat? All right, so what's my Q? I've got Q. It says 203 joules. Awesome, plug that in. Then do I have a mass? Yes, I do, 45 grams. Plug that in. With the G, always remember, get those units in there. Does it give me specific heat? No, it's asking for specific heat. Does it give me a change in temp? Absolutely, and I don't even have to do any math. It gives me 10 degrees Celsius, so I plug it in. So here's a simple thing that we talked about in class. Multiply on this side. Consider this like X and these Y. I can multiply the Y's together. So 45 grams times 10 degrees Celsius. It's going to be 450 grams degrees Celsius. It's on this side with my X. What do I got to do? I got to divide that on this side. When I do that, I come up with 0.451 joules per gram Celsius. Now, here's the thing. I could take this number, sorry, not yet. So this is my metal, my specific heat, and I'm going to guess it's definitely a metal because it's less than 1. All right, let's look at this next thing. 2,500 joules of heat are released, given off. When I give off, I got an exothermic thing going on from a 30-gram sample of water. Ooh, there's that water at 23 degrees Celsius. Okay. What will be the final temperature of the water? So this one is a little bit tricky. All right, it gives you all this information. It gives me 2,500 joules, giving me 30 grams. I know my water is 4.18. It also gives me part of the temperature. I'm not going to mess with the temperature yet. I'll wait to the end to make my life a little easier. So once I multiply these and then divide over here, I get a temperature of 19.9. All right, well, I originally started with 23.0 degrees Celsius. When I release, that means I give off, I'm going to end with something less than. So I'm going to do 23 minus 19.9. I should get 3.1 degrees Celsius. That is my temperature change. Cool. All right. So if there's no temperature change, to calculate the absorbed or released, we use certain formulas. Again, you can find them table T in the heat. So for melting, remember we call that freezing. You could also call it fusion on the other side, the cooling curve. So we're going to use the heat of fusion, which is joules per gram. There's no degrees Celsius. Why? No temperature change. Temperature stays the same. For fusion, this is going to happen down here on the freezing, melting, solidification, crystallization line, depending on if you are cooling or heating. For water, you've got 33.4 joules per gram on your heat of fusion. How do I know? Table B. There's my heat of fusion. So I did the freezing, melting. Now I got to do the opposite, my vaporization, which is this line up here. That's the heat required to vaporize 1 gram of a substance. And for water, it's 2260 joules per gram Celsius. Again, found in table B. You will notice this is more than that. Why? It's going to take more heat. Okay? Here's an exercise. What quantity of heat is required to change 50 grams of ice to liquid? Phase change. There's a phase change. It's dealing with ice. I know there's no change in temp. Even though they give me it, there's no change in temp. 0 degrees means ice, means heat of fusion. All I need to do is plug in the numbers. I've got 50 grams for my mass. Heat of fusion of ice or water is 33.4 or 33.4 joules per gram. Multiply those together, you get 1670 joules. Cool. All right. What quantity of heat is required to vaporize that same sample, 50-gram sample of water? Again, use my 50 grams, and I've got 2,260 joules per gram Celsius. Again, looking at table T. When I multiply those together, I get 113,000 joules per gram, joules. So note this, 1 gram sample of steam at 100 degrees Celsius has 2,259 joules more energy than 1 gram of sample of water at 100 degrees Celsius, which is why steam burns are worse than hot water burns. When you are dumping out that hot water, that boiling water, that steam hitting you burns more so than if you were to dump the water on yourself. All right, so here's another one that requires you an addition of both. All right, what quantity of heat is required to heat 25 grams of ice from 0 to 55? Now, why did I say twice? Well, I've got 0. That means I've got ice, which means I've got heat of fusion. So I got to do my heat of fusion first. How do I do that? I plug in my 25 grams. It is ice, meaning water. I got to add this, the 334 joules per gram. Multiply them together and I get 8,350 joules. This is the quantity of heat for ice. Now I got to get the temperature change from 0 to 55, which is right here. I got to do my MCAT. So heat, I got to find that heat. Mass, again, is 25 grams. Specific heat of water or ice is 4.18 joules per gram Celsius, find in table B. And then I've got a temperature change from 0 to 55. So 55 minus 0 is 55 degrees Celsius. Multiply these together, and I get 5,750. I'm done, right? No. I got to get the total heat. That means adding these two together. When I do that, my total heat is 14,100 joules. Cool. Last but not least, I've got this lovely little diagram, which you will see in your green pages. When I have this diagram, I can use all the information on here to help me figure out what's what. All right, so the accompanying graph shows the temperature of an 8-gram sample of substance heated at a rate of 100 joules per minute. If each one of these squares down here, these minute squares, represent 1 minute, and each minute is 100 joules, each one of these is worth 100 joules. First off, looking at this, what's my boiling point? My boiling point is this line here. So what's my boiling temperature? So I'm going to follow it straight all the way over, and I know my temperature is 90 degrees Celsius. Sweet. All right. What is my heat of fusion for this substance? And I've got all this stuff. You're like, how the heck did you get that, Miss Co? Well, my mass, off the bat, I know is 8 grams right there. Heat of fusion, remember, is this small line right here. How do I figure that out? Well, first off, I gotta know that right here, it takes 8 minutes. 1, 2, 3, 4, 5, 6, 7, 8. 8 minutes to heat this. And every one of those 8 minutes is 100 joules. So 100 times 8 equals 800 joules, which is how I got here. When I multiply this out, I get 10 joules per gram. All right. What is the specific heat of the liquid in the liquid phase? From here to here. Right there. So what I got to do is count again, and I get 9 minutes, so it's 900 joules. Again, what I would do is 10 times 35. I get 350 grams per Celsius. Divide that by 900, and I should get 2.57 joules per gram Celsius. All right, so table B, here's my table B. Don't forget to do the worksheet, heating curves and calorimetry. If you have any questions, please, please, please ask me. Besides that, I hope you have a great day